Imagine a piece of metal that can be bent nearly to its breaking point and still spring back perfectly every single time, with no scratch, no crack, no memory of the stress you just put it through. Now imagine that this metal has existed since 1960, that it beats steel on almost every measurable property, and that you have probably never held it in your hand. That's not science fiction. That's a real material sitting quietly in labs, in a handful of factories, and in a few very expensive products you've probably never noticed. Welcome back to Hidden Fix Lab, where we dig up the things that should have changed the world already, but somehow haven't. Here's the everyday problem most people never think twice about. Metal fails. Not eventually, not rarely. Constantly, predictably, and by design of its own atomic structure. Every wrench, every bridge cable, every hinge on your car door is made of a material riddled with microscopic weak points. Engineers don't fix this. They manage it. They add safety margins. They inspect for fatigue. They replace parts before they snap. Multiply that across every steel structure on Earth, and you start to see the real cost. Billions of dollars a year spent not on making metal stronger, but on babysitting its flaws. We've simply accepted this as the price of using metal at all, the same way we accept that shoes wear out or that phone screens crack. It seems unavoidable, except it isn't. Here's the part almost nobody talks about. There's a category of metal that skips this problem entirely, not by patching around the weakness, but by removing the thing that causes it in the first place. It's been sitting in materials science journals for over 6 decades, quietly outperforming steel in test after test, and yet it barely makes it into consumer products. Once you understand why, you'll start noticing the same pattern everywhere, not just in metal, but in almost every miracle material you've ever heard hyped up and then never heard from again. To understand why this metal is different, you have to zoom in, really zoom in, on ordinary steel. Under a strong enough microscope, steel doesn't look like a solid, uniform block. It looks like a mosaic, thousands of tiny crystal grains crammed together, each one facing a slightly different direction, like a floor tiled with mismatched shards of glass. Where those grains bump into each other, you get a boundary, and that boundary is a weak spot. That's where rust creeps in first. That's where a crack starts to form after 10,000 flexes. That's where, one day, after years of quiet stress, something finally gives. This isn't a manufacturing defect. It's simply how metal has always cooled and hardened, going back 3,000 years to the first bronze tools. Every metal you've ever touched, steel, aluminum, titanium, copper, is built this way, out of a patchwork of crystals with built-in seams. So back in the 1960s, a group of researchers asked a strange question. What if you could cool molten metal so fast that the atoms never got the chance to line up into those crystal grains at all? What if, instead of hardening into a tiled mosaic, the atoms froze in place while still jumbled, the way they were when the metal was liquid? That's essentially what glass does. Ordinary window glass is atoms locked in a disordered, liquid-like arrangement rather than a neat crystal lattice, which is part of why it's transparent and brittle in its own particular way. Apply that same idea to metal, cool it fast enough, and you get something scientists nicknamed amorphous metal, or more evocatively, metallic glass. No grains, no seams, no built-in weak points for cracks or corrosion to exploit. Here's why that actually matters in practice, and this is the simple science behind it. In ordinary steel, stress travels through the material and gets trapped at those grain boundaries, building up pressure in one tiny spot until something snaps. In metallic glass, there are no boundaries to trap it. Stress spreads out evenly across the whole structure, like weight distributed across a trampoline, instead of concentrated on one weak floorboard. The result is a material that can be roughly twice as strong as steel for its weight, with an elastic range, how far it can bend and still spring back, up to 10 times greater. It resists corrosion far better because there are no seams for rust to crawl along. And when it's cast, it comes out of the mold nearly finished, with a surface so smooth it barely needs machining. You'd expect a material like that to be everywhere, and in a few corners of the world it already is, just not the corners most people look at. Golf regulators actually banned certain club faces made from a zirconium-based metallic glass because the energy return on impact gave players an unfair advantage. A governing body decided the metal was, quite literally, too good to allow in competition. Apple has used it for components that demand extreme precision. Surgeons use scalpel blades made from it because the edge holds far longer than steel and can be sharpened finer. In every one of these cases, wherever performance actually outweighs cost, metallic glass wins outright. No contest. So here's the real question worth sitting with. If it's this good, why isn't it in your car, your kitchen, your house? The answer has almost nothing to do with the material's performance and everything to do with the mess of turning a lab success into a mass-produced object. First, there's the cooling problem. To lock atoms into that disordered state, you need an almost impossibly fast quench. And for decades, that only worked on thin ribbons, wires, and sheets, because the center of anything thicker cooled too slowly and crystals would sneak back in before it fully hardened. You can't build a car frame out of something thinner than a sheet of paper. Second, many of the alloys that do manage to form thicker, more useful shapes rely on exotic, expensive elements: zirconium, hafnium, palladium, some of which cost more per kilogram than gold, and a couple of which are genuinely tricky to handle safely. You simply can't build a bridge beam out of something priced like jewelry. But the deeper reason runs even further than chemistry and cost. Civilization, quite literally, was built around steel. Every foundry, every stamping press, every trained welder, every supply chain moving raw ore to finished parts. Trillions of dollars of infrastructure exist because steel got there first. Switching wouldn't just mean adopting a better material, it would mean rebuilding the machinery of industrial civilization from the ground up. And industries, like people, don't rebuild their whole world just because something slightly better shows up. They rebuild only when the old way stops working entirely, or when the new way becomes cheap enough that switching is basically free. This is exactly why the QWERTY keyboard layout, originally designed to slow typists down so 1870s typewriters wouldn't jam, is still what you're typing on today, even though better layouts have existed for almost a century. It isn't the best option that wins. It's the option that got there first and built the world's habits around itself. And metallic glass isn't alone in this trap. Graphene won a Nobel Prize back in 2010 for being hundreds of times stronger than steel by weight, while conducting electricity better than copper, and yet your phone still doesn't have a graphene battery. Carbon nanotubes were supposed to revolutionize construction and aerospace in the 1990s. Decades later, manufacturing them cheaply at scale is still an unsolved puzzle. The pattern repeats so often, it stops feeling like a coincidence and starts looking like a law. Discovering something extraordinary is the easy part. Making it cheap, reliable, and scalable enough to replace something the world already depends on, that's the actual mountain. Here's where it gets genuinely encouraging, though, because metallic glass isn't stuck the way some of these other materials are. It's already working quietly at industrial scale in a place most people never think about. Transformer cores and power grids, where thin, amorphous metal ribbons cut down energy losses compared to standard steel cores, running by the millions right now without any fanfare. Researchers have also been swapping out the exotic, gold-priced elements for cheaper iron and copper-based alloys, cutting costs dramatically without gutting performance. And 3D printing is starting to solve the cooling problem in a completely different way. Instead of trying to freeze a large chunk all at once, you build the object up in thin, controlled layers, each one cooling fast enough on its own. The wall is still there, but it's got real cracks in it now, and they weren't there 10 years ago. So, if you're wondering whether to expect metallic glass parts in your next car or kitchen appliance anytime soon, here's the honest, practical answer. Not yet, and probably not for a while in bulk structural uses, but it's already worth knowing about if you work with precision tools, electronics, or specialty equipment, because it's already available in blades, springs, and small precision components where the price premium is worth paying. If you're curious to see it yourself, start by looking up small commercial products, premium knives, specialty watch components, or high-end sporting equipment that advertise amorphous metal or liquid metal alloys. That's the easiest entry point to actually holding this material rather than just reading about it. Now for the honest limitations, because no material is a miracle and you deserve the full picture, not just the highlight reel. Metallic glass isn't a universal upgrade over steel. Under certain kinds of stress, particularly sideways shearing force, it can fail suddenly along narrow bands rather than bending gradually the way steel warns you before it breaks, which means engineers have to design around that behavior rather than treat it as a drop-in replacement. It's also still expensive and still limited in the thicknesses it can be reliably manufactured at, so for now it belongs in specialized, high-value applications rather than mass structural use. None of that makes it any less remarkable. It just means the manufacturing story, not the material story, is what will decide its future. And that, honestly, is the bigger lesson buried inside this whole topic. We love origin stories. The moment of discovery, the headline, the scientists create material stronger than steel. It's clean, it's exciting, it fits in 15 seconds. But the truth is messier and far more interesting. Discovery is the easy part. Manufacturing, scaling, and convincing an entire world already built around something else to change. That's what actually decides whether a breakthrough becomes real or stays a laboratory curiosity for another 65 years. The next time you hear about some incredible new material that's about to change everything, remember metallic glass. It already changed everything, technically, decades ago. It's just still waiting for the world to catch up. That's Hidden Fix Lab, where the real story was never the discovery. It was always what happens after.